electronic circuits. So we have started with common emitter amplifier configuration, and let me revise what we have done so far. So all of you can draw along with me. So we were discussing common emitter amplifier, and here is the circuit. I'll take 5 minutes to revise what we have done. So please draw the circuit diagram along with me again. So this first we draw the voltage divider bias. All right. So this is my voltage divider bias. This voltage divider bias will make so that BJT is on and it is working in the forward active region. This is my biasing resistors R1 and R2. Then we have RC and then we have RE. Now for it to convert into an amplifier, we have to apply the input at the base and sense the output at the collector. So before connecting it to a source, we have to connect it to via capacitors. Why we require capacitors, anyone?
Sir, to block DC signal.
Yes, to block DC. So here are all the capacitors connected. There are 3 capacitors. This is CC1, CC2. These capacitors are input coupling capacitor and output coupling capacitor. This CE is my bypass capacitor. So here is my source. This is RS. This is my supply plus minus VS. And this is your ground. All right. And here we have output where we have connected a load. So this is RL and this is my plus minus V out. All right. And this is my NPN BJT. NPN BJT. Okay. So this was my configuration. Now in this configuration, what was my source? So
Yes.
this part is my source. This is my amplifier. And this part's what was my load. All right. And why it is called as common emitter? It is called as common emitter because input is applied to the base. This is the input applied to the base and output is sensed at the collector terminal. So that's why it's called as a common emitter amplifier. Now, there are 2 types of analysis over here. DC analysis we have seen. So in DC analysis, all the capacitors will behave as open circuit. And in AC analysis, we consider them to be short circuit. Okay, because the reactance of the capacitance is very, very low at mid frequencies. So let's begin with the AC analysis. Let me recap by how we do it. So in AC analysis, we consider all the DC voltages will be short circuited. AC analysis means small signal analysis. So I've already told you all, small signal analysis means we will only have small signal time varying quantities. We will not have any DC voltages. All right. So your DC voltages you have to short circuit and all the capacitors you have to also short circuit. So how will the diagram look like? So you have this resistor over here. This will go to ground because power supply is short circuited. Okay. This is also ground. This is RE, RC, R1, R2. All right. And over here we have this capacitor will be short circuited, behaving as short circuited. Then we'll have RS and supply VS. And here what do we have? Here we'll have emitter terminal going to the ground. And here we'll have output. This again a capacitor RL. Here is my V out. Okay. I think we have already drawn this. So now what do we do? Anyone? Now the next step is we replace BJT, which is over here, by its hybrid pi model. Is it not? Yes or no?
Yes, sir.
Yeah. We'll replace the BJT by its hybrid pi model. So what do we do is, we'll first of all highlight the terminals. This is collector, this is base, and this is emitter. So first we draw the hybrid pi model. So hybrid pi model is as follows. So here you have, first draw the base, then the collector and emitter. So between base and emitter, we have resistance R pi, the internal resistance of the BJT. Between collector and emitter, we have a current source, which is representing IC, which is GM into V pi, where this is plus minus V pi. Okay. And between collector and emitter, to include the early effect, we have output resistance of the BJT, which is RO. All right. So this is my, and this is my emitter terminal. This is my hybrid pi model. Okay. So now we connect the external thing. So at the base terminal, we have R1 and R2 in parallel. So here we have it, R1 parallel to R2. All right. Then we have RS over here, and then we have a supply over here plus minus Vs, or we can connect it as a source only. All right. Plus minus Vs. This will be, yeah, this will be V in actually. We can call it V in. Okay. And what about the emitter terminal? Emitter terminal, we have a resistor RE and a parallel short. So actually the parallel short, when it comes to a parallel with a resistor, it is a short only. This RE becomes redundant. So emitter terminal will be going to the ground. What about a collector terminal? Collector terminal, we have RC going to the ground and RL going to the ground in parallel. So first we have RC, then we have RL, and then we have plus minus V out. Here it is. All right. So this was our, what is the name of this circuit called as? This is small signal equivalent circuit of BJT common emitter amplifier. All right. Now looking at this circuit, we have derived a voltage gain. So our aim is to find first voltage gain expression, second input resistance of the amplifier, and third output resistance of the amplifier. I hope you're writing along with me. Anyone facing any problem up till now? Or you're following this? We have done this yesterday only. I'm repeating it because it's important. Everyone clear about it?
Yes, sir.
Yes. Okay. Now we have to derive AV. So we'll derive AV very, very quickly because we have done that already. Okay. So for deriving AV, what do we do is we need to apply KCL at the collector node. So here over here, we'll apply KCL at collector node. So this is one and the same point. Okay. So this is the current GMV pi. What about this current over here? This current, this is V out voltage, which is in parallel with it. So this will be V out upon RO. What about this? This will be V out upon RC, and this current will be V out upon RL. I hope you are getting it because the voltage is constant and we have a resistance. So current will be voltage upon resistance. So applying KCL, we have done it, but we are doing it one more time. We are deriving AV, which is V out upon Vs, which can be written as V out upon V in and V in into Vs. Why? Because what is V out upon V in is the voltage gain of the amplifier, excluding the source side. So this is AV, this is AVT. And what about this V in upon Vs? This is including the source, internal source resistance. Ideally, Vs and V in should be same. But since we have a small source resistance, these two are not same. So that's why. All right, so let's find out V out upon V in. So we need a equation relating V out and V in terms. So we'll apply KCL at node C. What do we get? All of these currents are outgoing currents, as you can see, outgoing, outgoing, outgoing. So we'll add them together. So Gm into V pi plus V out upon Ro plus V out upon capital RC plus V out upon RL is equal to 0. Agree? Yes or no? And also from the diagram, can you see this V pi and V in are same? So we can write over here, they are in parallel, right? So V in is equal to V pi. So here we can modify the equation as follows. Gm into V in minus Gm into V in will take it on that side. Then rest all the other things, V out common. It will be 1 upon Ro plus 1 upon RC plus 1 upon RL. Okay. This is nothing but minus Gm into V in. This is V out divided by these three resistors are in parallel. So it will be Ro parallel to RC parallel to RL. I hope you are getting it. Now if I equate V out upon V in, what do we get? Minus Gm into Ro parallel to RC parallel to RL. All right. And this becomes my voltage gain. This becomes my voltage gain excluding the source. Now there can be other three cases over here. This we have not discussed yesterday. So if Ro is not present or Ro is infinite, now how will be the formula will be? So AV will be minus Gm into RC parallel to RL. Getting it? And if RL is not present, RL not present, if the load is not present at the output, then what will be the formula? AV will be minus GM into RC alone. So these are the modifications. Okay. And this will be equal to total gain. So AVT will be equal to AV if RS is 0. Okay. So in this expression, in this diagram, if the source resistance, internal resistance is 0, then Vs will be equal to V. If they are not equal, then what will happen is, what will happen now? Tell me. I'll dividing this again. I'm representing this again. So how the diagram will looking like over here like this. We have RS and here we have the amplifier and we have Rn of the amplifier over here. Rn. This is Rn, internal your input resistance. So here we have marked V in and here is my Vs. Correct? I mean, let me draw it as a source itself. Now, what is the relation between V in terms of Vs? So by voltage division rule, V in is Rn upon Rn plus Rs into Vs. So what will be V in upon Vs? Will be Rn upon Rn plus Rs. And this factor should always be less than 1. Ideally equal to 1 if here we have written, right, AVT is equal to AV if RS is equal to 0. So if RS is equal to 0, Vin is equal to Vs, and that is where you have this result. Okay. So what will be the total gain? Total gain AVT will be, so total gain over here, AVT will be how much? Vin upon Vs into V out upon Vin. Okay. This expression we know this is Rn upon Rn plus Rs into what was the gain? Minus Gm into RC, RO, right? RO parallel to RC parallel to RL. Okay. So intermediately, this is the formula for common emitter amplifier. So this is what we have derived yesterday. And what does the negative sign indicate? Anyone?
Inversion.
Yes. Negative sign indicate that input and output are 180-degree out of phase. And if someone tells you to plot the graph, then how will you plot the graph? You'll first draw the input versus time. So let's say if this is my input, so how my output will be out of phase and with a higher amplitude, like this. Okay, so this is my V out of T, and dotted line is my V in of T. Voltage versus time and input, input versus time and voltage versus time, output voltage. All right. I think this much we have completed yesterday. Yes or no?
Yes, sir.
Okay. Now we'll proceed ahead. So next we'll derive, write down. Next we'll derive input resistance. So that was the revision, what we have done yesterday, overall of it. So this is Rn. Yesterday I told you what is the significance of Rn. Rn should be very, very high for a voltage amplifier, and output impedance should be very low for a voltage amplifier. Now we have to derive this input resistance. So what do we do in the input resistance is, what we do over here is, we have the circuit with us. Okay. And at the input of the circuit, at the input terminals, you connect a test source, Vx. Okay. And you find the current flowing through it, Ix. Okay. So what will be the input resistance of the entire circuit over here? Can anyone tell me? So Rn will be Vx upon Ix. So put the entire thing inside the box. We don't care what is at the output. At the input side, include a test source. So this is my test source. So because of this voltage source, will have a current flowing into the circuit. So you find out the expression of Vx upon Ix, and there you have it. Okay. So for this, we need to draw the small signal equivalent circuit again. So I'm drawing it directly over here. So we have first base. It will be a practice for you all. If you draw it again and again, it will become a part of you. So emitter terminal was grounded, as we know. Between base and emitter, we have R pi, right? Correct? And here we have V pi. What do we have over here? GM into V pi. Yes or no? And then it followed by three resistors, that is RO. Then we have RC, RL, and here we'll have V out. All right. And at this side, what do we have? R1 parallel to R2. Yes or no? And over here, what do we have? RS, and here it will be VS. Okay. Yes. Yes or no? So,
Yes.
so how do we apply this method? You put entire circuit inside the box. So I'll put entire circuit from here. This is my input terminal, right? I'll put the entire circuit inside the box like this and apply the external voltage. Now disconnect my source. So I'll disconnect my source. Okay. And apply a test source outside. So if you apply a test source outside, how the circuit will become? Like this. So this is my test source. Let me do it over here. So this is my external test source Vx, and I have my current Ix flowing through it. Okay. And we have R1 parallel to R2. Then we have R pi. These are both going to the ground. Acha, what happens between base and base and collector? Do you think why base and collector are not connected to each other? Anyone? Anyone, can you recollect? Why base and emitter are not connected to each other? You remember base collector junction is reverse bias. And reverse bias means it's a very high resistance, right? Therefore, it's an open circuit. As you can see, between base and collector, it's open circuit. No current flows from base to collector in the above circuit. So no current flows from base terminal to collector terminal. Are you getting it? Yes or no? Hello.
Yes, sir.
Yeah.
Yes, sir.
And what is the impedance shown by the, what will be the impedance of this current source? Do you know what is the impedance of a current source? Impedance seen by the current source. We have seen now we have a voltage source and a current source. So if you have a current source, it will have a very, very high internal resistance. Yes or no? So if this is Rn, this is In, this is very, very high. And now we are doing the analysis. So very high will be determined as the impedance of this voltage source. What I'm saying is it's infinite. So this current source, this current source, voltage dependent current source will be infinite. It will be become open circuit. All right, because there is no current now flowing between. See here, no current is flowing between base and collector, so they are disconnected, right? And we cannot analyze any current over here. Acha, will the current base current flow into the collector now? Yes or no? Is there a connection over here? No, na, open circuit. So this will become redundant. This will become redundant. There is no current flowing into the collector terminal. So therefore, this Ix, does it flow to collector current or base current?
Base.
Answer is simple. Yes, correct. So current Ix flows into R1 parallel to R2 branch and R pi branch. Does it flow into the collector terminal? No, because it's open circuit over here. And I've written why it is open circuit. Because base collector junction is reverse bias, no current flows from base to collector in this situation. So how the diagram will be now? How is the diagram reduced to? Anyone? So here we'll have a voltage source plus minus. This is Vx. We have R1 parallel to R2. And what do we have next? R pi. So the entire circuit got reduced to this network. Yes or no? And this is
Yes.
Ix. Yeah. Now tell me what it is, Vx upon Ix directly if you want to find out what it is. Come on. So what is Vx upon Ix? Simple Ohm's law. It is R1. What do
R.
you see over here? Parallel to R2, then parallel to R pi. Is it not?
Yes, sir.
Yes or no? So therefore, my Rin, the input resistance of the amplifier will be R1 parallel to R2 parallel to R pi. Got it? Yes or no? So this is my input resistance of common emitter amplifier without the source, internal source. Now, if you connect back the source, resistance, now we have ignored, now here, RS we have ignored. So including RS, we get. So if I include RS, what do we get over here? Anyone? So if this is my RS and this entire thing is my RN, I'm calling it RN now. Okay. And this is my VX, let's say. This is Vx and this is my current flowing Ix. Can you tell me now what will be, Rn? This is Rn of including the source. So RNS. What will be RNS? What is RNS over here? Come on. Plus, na plus. They were in parallel. This is plus, right? So what it will be? RS plus Rn. So Rn including the source will be what? Rs plus R1 parallel to R2 parallel to R pi. Okay, so this is the input resistance of the CE amplifier including the source resistance. So this has getting added. The source resistance got added from this expression. Are you getting it?
Yes,
Yes,
sir.
no, what? Okay, clear. So we have determined, we have derived actually the input resistance of the amplifier. And I told you the importance of input resistance. It should be very, very high. Okay, let me go to. All right. Can I move on to the output resistance, students? Yes.
Sir, can you explain why the um, collector doesn't get current?
Yeah, base emitter junction reverse bias, right? Reverse bias PN junction, does the current flow? No,
No.
no. So
Okay.
here it is open circuit. Now see, base and collector are not connected, as you can see in the hybrid pi model. So this current Ix will flow in this branch, right? Will flow in this branch, but where it will go over here? Not nowhere, right? That's why this part of
Hmm.
the circuit entirely gets removed.
Okay.
Current doesn't flow to this, so it will flow in these two branches only. That's what I've written over here. That's why we are doing the analysis over here. This is input resistance.
Okay.
Okay. Now, shall we go to the output resistance derivation? So please write down the heading, everyone. Output resistance R out. Okay. So for the output resistance, again, we consider the entire circuit. So this is my entire circuit. There is a method also. Here we have a condition that you make input source equal to 0. So you make input Vin equal to 0. Short circuit the input. Okay. And at the output terminals, you connect a test source again, plus minus Vx. And due to that, current Ix will flow. So what will be my output resistance over here again? So R out will be Vx upon Ix. Okay, so this is my R out, is my output resistance. So write down from here. So for calculating R out, we short circuit input source. So let's do that over here. Let us draw that circuit again. So how was that? Base, collector, emitter. Emitter is grounded. Between base and collector, what do we have? R pi. Between collector and emitter, a current source, GM V pi. This is plus minus V pi. And you will have RO. Then you will have RC. Then RL. RL is my load. Okay. So this is the network. And what about here? This will be R1 parallel to R2. Here it is RS. And here is my supply voltage. VS. Okay, this is RS. So what was this thing? You connect everything over here, connect the entire circuit out inside the box. As you have seen over here, we have to short circuit the supply V in. So short circuit the source means this, you short circuit it. Okay, so VS will be 0, right? If VS is 0, what about V in? What about V in? V in also 0, na? Are you agree to it? Yes or no? Then at the output, you will connect a test source over here. So let me call that test source as Vx and this is Ix. Okay. Now, if if Vs is 0, then Vin is 0. Can I say V pi is 0? Looking at this. So here we have Vs as 0. That implies Vin is 0. Does that mean V pi is also 0? Yes or no? Because Vin and V pi are parallel, right? Are you getting it? Yes, no.
Like,
So what happens to GM V pi? that also becomes 0. This means that the current source becomes 0. When is the current source deliver 0 current? So during that time, that means my current source over here, GM Vpi is also 0. So this Vpi is 0. GM Vpi is also 0. 0 current is represented by open circuit. Yes or no? So therefore, the current source GM Vpi is replaced by open circuit. So how does the circuit reduces to? Agree, na? So this becomes 0. This becomes 0. Okay. So how my circuit will look like? This is 0. This is grounded. Vin is 0. Vpi is 0. GM Vpi is 0. So entire circuit from to the left hand side of this collector, let me highlight with dotted line. To the left hand side of this dotted line disappears. Why? Because everything is 0 here. So what we are left out it was this. So this is becomes open circuit. Let me draw it and show it to you. This is my current source. So on the left hand side, everything goes. We have RO, we have RC, RL, and then we have a source, test source Vx and Ix. So this is my circuit now. Do you agree why this is 0? Because Vpi is 0. Why Vpi is 0? Because Vin is 0. Why Vin is 0? Because Vs is 0. Agree to it? Now, what do you see over here? Do you see all three resistance as parallel? Yes or no? So what is Vx upon Ix? Can you tell me? It will be Ro parallel to Rc parallel to RL. Got it? And what is Vx upon Rx? We have determined it is the output resistance, R out. So R out will be equal to Ro parallel to Rc parallel to RL. Understood this or no? Any
Yes,
doubts
sir.
over here, anyone? Anyone having any doubt? This is the output resistance of common emitter amplifier. All right? Yes or no?
Yes, sir.
Okay, great. So let us summarize and write down all the formulas related to the common emitter amplifier, whatever we know. So this is what we have done so far. We have started with common emitter amplifier, okay, and we have derived the expression of AV, the total voltage gain AVT. Then we have plotted the input-output waveform. Then we have derived the expression for Rn, which was R1 parallel to R2 parallel to R pi. If Rs is not present, if Rs is present, it will be Rs plus this term R1 parallel to R2 parallel to R pi. All right. Then we have R out equal to RO small ro parallel to RC parallel to RL. All right. So now let me give you a summary because this will help into help solving numericals easily. So we have common emitter amplifier. All right. And first you do the DC analysis. So this is the procedure to follow. So first thing you do is DC analysis. So from the DC analysis, you find out what VTH first. First parameter is VTH. Then next is RTH. Next will be IBQ followed by ICQ. Then you find out VCQ is not necessary. Okay. So you found out ICQ, right? Now from ICQ, you do something called as small signal analysis. So you find small signal parameters. Small signal parameters. So these all things we already know. This is DC analysis. These all things are DC analysis. What do you mean by small signal parameters? How many small signal parameters are there? Anyone? Hello. GM
EV,
is there.
RL, RO.
Yeah, GM is there. GM. So it's calculated by VCQ upon VT, right? Then R pi is there, which is beta upon GM. And what is RO? VA upon ICQ. What is VT over here? Thermal voltage, which is 26 millivolt at room temperature at 27 degrees Celsius. That is fixed. VA will, so what all things should be given to you in a numerical? Beta should be given. Okay. Beta will be given to you and VA. VA is called as early voltage. So remember, if VA is not given, VA is not given, then assume RO, the output resistance is infinite. The RO is infinite. Very, very important. If early voltage is not given in a numerical, RO is infinite. So normally your beta is always given to you. Okay. So next you do small signal parameters, right? And then after that, you plug in the formulas in actual AV. You draw. After this step, what is it? You draw small signal equivalent circuit like we have drawn 3 times today. So draw the small signal equivalent circuit and then you derive AV. You know what is the formula for AV? Let's say if I exclude RS, let's say RS is 0. So what is the formula? Minus GM RO parallel to RC parallel to RL. It may happen that VA is not given, so RO also will disappear. So if RS is present, then what is the formula? AV will be, AVT will be, what is it? Rn upon Rn plus Rs into AV, this AV. Okay. So next, what do we find out? Tell me. Rn. So what was the formula? R1 parallel to R2 parallel to what it was? R pi. Now, if we have given the value of Rs, then what is the formula? RNS. It will be Rs plus Rn. This value of Rn. Then the last thing what we need to find out is R out. R out. What was the formula? RO, small RO parallel to RC parallel to RL. So this is the entire summary. How do we solve a numerical? And if a numerical on common emitter amplifier is asked in the exam, it will be asked for 10 marks only. Is that fine, everyone? Can we start with the analysis?
1 minute, sir.
Yes. You're writing it down something?
Yes, sir.
So this is the procedure we need to follow, and it's a very famous numerical. You know, sometimes in the numerical, the Q point is given, or the small signal parameters are given. Like for example, they can give you GM directly. So in that case, no need to solve DC analysis. You can directly substitute the formulas GM, R pi, and RO. Sometimes they give it a value of R pi and GM in the numerical itself. So you need to use those formulas and directly jump to calculating AV, Rin, and R out. Can we start with a numerical, everyone?
Yes, sir.
All right, let's do that. So write down, everyone concentrate, numerical number 1. Write down, find the voltage gain input resistance and output resistance of given amplifier circuit. All right. So draw the amplifier circuit, please. So we have CC1 over here. Then we'll have CC2. Here we have V out. This is RL. Then we have the capacitor over here. These all go to the ground, and we have a voltage source, V in. This is supply VCC, R1, R2, RE, RC. The values I'm writing it down. This is 1 microfarad. This is 100 microfarad. This is CE. And this is 1 microfarad. It doesn't matter what the values of capacitors are right now. Right now, we are only interested in the values of R1, R2, R2. This is 90 kilo ohm, R1. R2 is 10 kilo ohm. RC is 2.2 kilo ohm. And RE is 680 ohms. Always remember, in voltage divider bias, R1 should be greater than R2, which should be greater than RC, should be greater than RE. And beta is given as 210, and early voltage is given as 100 volt. So this is the given data. And supply voltage is 16 volt, plus 16 volt. All right. Can we start?
Sir, 1 second.
Okay, I'm starting now. So let's start with the solution. So write down step number 1, DC analysis. So what do you do DC analysis? All capacitors are replaced by open circuit. So open circuit, all capacitors. So what will the circuit look like? Circuit will look like a voltage divider bias. Like this. So this is VCC, R1, R2, RE, RC. So this is going to the ground. Here it is. This is my circuit. Now you know we cannot apply KVL at the input loop. So what do? We apply Thevenin's theorem at the base, and the circuit in short looks like this. We have done this before, so I'm not repeating the step here. So finally your circuit will look like this. So you will have RTH, you will have VTH over here. This is RE, this is RC, and this is VCC. Yes or no? And this is ground. Okay. Here what do? We mark the terminals, or we can write over here VB. This will be plus minus. VCE is not necessary right now. So this is current flowing over here, which is current flowing over here is IB. Here it is IE, right? And how is IE related to IB? It is 1 plus beta times IB. I hope you remember. And this is IC. Okay. Now what do we do with this data? So from this circuit, you need to determine how much is VTH. So tell me, this is point number 1. What is the formula for VTH? It's R2 divided by R1 plus R2 into VCC. So how much is R2? 10 kilo ohm divided by 10 kilo ohm plus 90 kilo ohm into VCC. VCC is 16. So can you tell me how much is this number? So it's basically 10 divided by 100 into 16. Anyone with the value of VTH? VTH? 1.6, right? Yes or no?
Yes, sir.
Okay, always remember, it's a caution. VTH is always less than VCC. Yeah? Remember, if you're getting some weird value of VTH, then it's wrong. If VTH is coming greater than VCC, then it's wrong. So VCC was 16 volt. This is around 1.6 volt. Always, always less. VTH is a fraction of VCC. All right. Next thing we do is we calculate what? Next, anyone? RTH. How much is RTH? R1 parallel to R2. That will be 90 kilo ohm parallel to 10 kilo ohm. Yes or no? So you know when two resistance are in parallel, the answer will be lesser than the least resistance. So RTH will be lesser than 10k for sure. How much is this? Is this 9 kilo ohm?
Yes, sir.
Okay, very good. Now what we do is I'm solving point number 3 over here. Now what do we do? Don't remember the formula for the input loop KVL. Now we apply KVL to base emitter loop. That means you are applying the loop KVL over here in this loop like this. So what do we get? Tell me. VTH minus IB into RTH minus VB minus 1 plus beta times IB into RE is equal to 0. If you can remember the formula for IB, well and good. So IB formula is IB will be given by VTH minus VB upon RTH plus 1 plus beta times RE. So either you can remember this formula, you can derive it in one step. It will be easier to derive. So this is the formula. How much is VB? 0.7, right? Yes or no?
Yes, sir.
Now this is point number 3. Have you completed up till here? Can I go down?
Yes,
Can
sir.
I scroll? Yeah. So I'm continuing here, point number 3 from here. I'm rewriting the formula for IBQ. It is VTH. Many students make a mistake of writing this as VCC. Then it becomes wrong. It is RTH plus 1 plus beta times RE. Always write the numbers over here. Okay. So this will be 1.6 minus, it will take one more step, but it never go wrong. RTH is 9 kilo ohm, so 9 into 10 is to 3. Then beta is, how much is beta? I think beta is 210, right?
210.
So it will be 211 because it is 1 plus beta. And RE is 680 it is? 6, let me check.
Yes, sir.
Is it
Yes, sir.
680? Now, give me the answer in microamperes. You might get answer as 10 raised to minus 5. Convert it into 10 raised to minus 6 and give me the answer.
So it's 5.90.
Yes,
Okay.
it's 5.9. Correct it is. It's 5.9 microamperes. Always IB is always in microamperes, right? In microamperes. If you're getting in milli, that is wrong. So you need to check the step. So these are the self-correcting things which you have to do. What is ICQ in terms of IB? Beta times IBQ. So multiply this 5.9 microampere with 210. Now ICQ is always in milliamperes. So tell me how many milliamperes? Milliamperes means 10 raised to minus 3. How much? 1.239. Just check.
Yes, sir.
Okay. You should not make any mistakes over here, because if you do the mistake at the initial step, then everything else what you do over here from now on will be wrong. So now we'll go to step number 2. Step number 2 is small signal parameters. We have to find out what are they, GM and all that, right? So first we'll find out GM. What is GM? ICQ upon VT. How much is VT? 26 millivolt. So ICQ is 1.239 into 10 raised to minus 3. VT is 26 into 10 raised to minus 3. So tell me the answer. GM unit should be always in milliampere per volt. So tell me in terms of milliamperes. How much is this? You have to do 1.239 divided by 26. How much is that coming? 47 point something? Just check your answer. Is it 47.67?
47.653.
Yeah, okay, nearby. 653 or 6. That's fine. But you're getting this answer, right? Now, what
Yes,
do we
sir.
do next? What do we do next? R pi. What is R pi? Beta upon GM. Yes or no? So beta is 210. GM is just now we have found out 47.65 into 10 raised to minus 3. So this R pi always will be in ohms, or if it is in kilo ohms or ohms. So tell me how much is this answer? Is it 4.4 into 10 raised to 3? Or we can write 4.4 kilo ohms. Is this the answer you got? Yes or no? Hello.
Yes, sir.
One second. Yes, sir.
Next is RO, which is VA, early voltage upon ICQ. VA is 100 and ICQ is 1.239 into 10 raised to minus 3. RO will also come in kilo ohms, always. So let me know this answer. How many kilo ohms? It will be 80.68. Please check.
I got 80.71.
That's
Yes.
fine. Yeah, it's fine. 80.71 because see, everyone admits, I mean, enters the value as two digit after decimal or 3 digit or 4 digits. So the answer will slightly vary. That is fine. 80.71, right? Yeah, that is fine. That is minor, this thing. Even if you get 79, it's acceptable. Even if you get 81, it's acceptable. Now, what was the next step? Come on. What is the next step? Draw
Hybrid.
Small signal.
small signal equivalent circuit, including the hybrid pi model of the BJT. So draw it, please. So what do we have? Base, collector, emitter is the same circuit, right? As we have studied. No change, right? Only RSig is not there. Yes or no?
Yes.
RSig is not there. So our analysis becomes simpler. So between base and emitter, what do we have? R pi. Yes. So quickly draw it. This is R pi plus minus V pi. Here we have is GM into V pi. RO is present? Yes. RC is present? Yes. Is RL present? Yes. So this is RC, RL. We have V out over here. On the input side, we have R1 parallel to emitter is grounded. Here we have R1 parallel to R2. And here we have no RS, right? We have directly connected a source, which is V in. So remember Vs is equal to V in over here. It's the same thing over here, right? So this is also V in. So there is no RS. Our analysis becomes simpler. Completed this? Yeah?
Yes,
Yes
sir.
or no? Okay. Now don't calculate AV. Huh? Please listen to me. Don't calculate AV. Calculate first Rn and R out. So how much is Rn formula without Rs? R1 parallel to R2 parallel to R pi. Do we know the value of R1 parallel to R2? Yes. How much it is? RTH. How much is that? 9 kilo ohm. Yes or
9
no?
kilo.
So we have to do 9 kilo ohm parallel to what is R pi? 4.4 kilo ohm. So give me the answer of 4.4 parallel to 9 kilo ohm. Is it 2.95? Just check. Yes or no?
2.95. Yes, sir.
Yeah.
Yes.
Then the next step will be R out. What is the formula for R out? RO parallel to RC parallel to RL. RO is how much? 80.71, right? 80.71 K parallel to RC. How much is RC? 2.2 K, right? Parallel to RL. How much is RL? 10 kilo ohm. Wait, huh? Just wait. RL was not given. It is 10 kilo ohm. Please add the value of RL as 10 kilo ohm, everyone. Okay. So what will be the answer? What should be the answer? Lesser than the least, right? So the answer should come out to be less than 2.2 kilo ohm. Agree? So let me know the answer. Is it 1.76 kilo ohms? Please confirm. It's heavily, calculation intensive numerical. Yeah. Hello. Did you get it?
Yes, sir.
Yes,
One.
sir.
Okay. The next step will be step number 10, AV. What is the formula? Minus GM into RO parallel to RC parallel to RL. Is it not minus GM into R out only? Yes or no? R out we have
Yes, sir.
just now calculated. That's why I told you calculate it last. How much is GM? 47.65. So it is minus 47.65 into 10 raised to minus 3 into 1.76 into 10 raised to 3. So this 10 raised to minus 3 and 10 raised to plus 3 will get cancelled. So multiplied is 47.65 into 1.676. How much do you get?
Minus 83.86.
Minus 83.86.
86.
That is your answer. That is your answer. Okay. I'll give you the weightage of marks also for this. So to get these values, you have 1 mark. To get the value of IBQ, 1, 1, 4, 5. These two are 1. This is 6. Sometimes they give marks for drawing the circuit also. Then how much did you get over here? 1, 2, 3, 4, 5. 5, right? This is 1, 6, 7. And AV has maximum 3 marks. Got it? So these are your marks. 10 marks distribution. All right? Everyone understood?
Yes, sir.
Yes, sir.
Okay. So please solve this. Now I'll give you numerical number 2. Everyone has got the answers. So as you can see, around 3 pages it took to solve this, but it's systematic. It's same. And the common emitter amplifier numericals are very, very famous. Okay. Next, numerical number 2. This I'll let you solve. I'll give you 5 minutes to solve this. Write down for a common emitter amplifier, R1 is equal to 40 kilo ohms, R2 is equal to 10 kilo ohms, RC is equal to 4 kilo ohms, RE is equal to 2 kilo ohms. Okay. VCC is 20 volt. Circuit diagram is not given to you. You have to draw. Then beta is 100. R1 is 40 kilo ohm, R2 is 10K, RC is 4K, RE is 2K, VCC is 20 volt and beta is 100. Find AV. That's it. Find voltage gain AV. Okay. So you need to draw the circuit and find out everything. Here, additionally, one more data is given to you. Okay. Here, they have given RPI also. RPI is 1.655 and GM is given to you 60.4542 milliampere per volt. So tell me, and if you want to find AV, tell me if they have given the value of GM and RPI, do we have to do the DC analysis? Do we need to find VTH, RTH, IBQ, ICQ? No, na, because
No, sir.
GM and RPI is directly given. Okay, so what you do is I'll give you 5 minutes. I'll take a break of 5 minutes and you have to solve AV and let me know the answer. You have to draw the circuit diagram. So is RS present? No, na. So RS is 0. Yes. Is RL present? No. Yes or no? So is VA given to you? No. So RO is also not given. RO is considered infinite. Okay. So it's become very, very simple. So can you tell me what will be the formula for AV? Directly minus GM, RO parallel to RC parallel to RL we do na. So how much we take? AVS minus GM, RO is infinite, RL is not present. So what it is? What it is? Minus GM into, come on, RC. That's it. Also find RN and R out. Yeah, that will be good. So take those 5 minutes, draw the circuit diagram and keep it ready and calculate this and let me know the answer. I'll be back in 5 minutes by 12:45. So please solve this and keep it ready. Once I come, you have to tell me the answer. Hello, have you completed? Yeah,
Yes,
students.
sir.
Okay,
Yes, sir.
so just let me set up my laptop. Okay, so what is the answer of voltage gain AV?
So minus 241.68.
Minus 241. Yeah, perfect. So yeah, wait a second. So which formula have you used? Minus GM into RC.
EMRC.
But prior to that, have you drawn the circuit diagram once? Don't directly use the formula. You have to draw the formal procedure. So it's minus 60.42 into 10 is to minus 3 into RC, which is 4 into 10 is to 3. So AV comes out to be minus 241.68. That's correct. How much is Rn? R1 parallel to R2 parallel to R pi. How much was it? Yeah, anyone calculated?
I got 1.37 kilo ohms.
It might be correct because it's lesser than this. So 1.37. Anyone got 1.37?
Yes, sir. I also got 1.371 kilometers.
Okay. Then R out is equal to
Uh,
anyone?
RC.
Perfect. It is 4 kilo ohm. Why? Because RO is not there. RL is also not present given to you.
So it
So
is
as you
only
can,
R.
yeah, it is RC. So as you can see, this complex looking numerical can become extremely simple also sometimes. Okay. Yeah. Now we have last 10 minutes. We have, I'll give you the results for one more configuration and then we'll leave for today. So next write down common emitter amplifier without bypass capacitor. Okay. So what does that mean is we have this voltage divider bias. So here we have input and output coupling capacitors, but bypass capacitor is not present. How will it affect the gain and everything? So we have a capacitor over here. This is my supply. Let's say Vs is not present. This is directly V in. We have R1, R2, RC. Here we have my output coupling capacitor. And let's say V out is also not there basically. So we have, I mean, RL. RL is not present. So we have only V out. Here RE. So this CE which was connected over here is missing. Or it is also called as, this configuration is also called as degenerated common emitter amplifier. Or it is
So,
also called as, yeah, sorry.
is there any difference if we make the capacitor like just two lines or one line and one curve?
Yes, the difference between this capacitor and this capacitor is, this is non-polarized, this is polarized. So the straight line indicates positive, this indicates negative. Understood?
Okay.
Yeah. Yeah. So let's do that. So here for the analysis, we assume RO is infinite. We assume it. RS is also not present over here. So I'm not deriving the derivation, but I'm directly writing the formulas. What will be the formulas? I'll show you the derivation because it is a lengthy derivation. So first of all, what will be the AV formula you will get is as follows. AV is V out upon V in, which will come out to be approximately equal to minus RC upon 1 upon GM plus RE. Okay. So the consequences from the with capacitor and without capacitor. So without capacitor, the gain has reduced. AV has reduced, but it has become more stable. But it is more stable. So this is the formula for AV. If you substitute R equal to 0 in this formula, what do we get? AVS minus GMRC. Yes or no? Are you understanding? So if RE is 0, it will become minus GM into RC only. Same thing only. What about RN? Does RN gets affected? Yes. So see, RN original formula is what? R1 parallel to R2 parallel to R pi. Now if you remove the capacitor CE, this additional term will be added. See here. It will be plus 1 plus beta times RE. So can you tell me what has happened? Has Rn increased or decreased?
Increase.
Yes. And is it good for a voltage amplifier or no?
Good.
Yes. Because Rn, higher the value of Rn, the lower is the loading effect at the input. And what about R out? R out remains the same. So what was the formula for R out? In this case, it is RC. It remains same. Rest all the analysis remains same. So what if we have RL connected? Agar RL connected hai in here, let's say if RL is connected over here, how will it affect the formula? So this will become RC parallel to RL. Are you getting it? Yes. And this will become, instead of RC, it will become RC parallel to RL. Did you understand? If RL is connected. Okay. Yes or no?
Yes, sir.
Okay. Now from the above numerical, this is I'll show you the derivation in a bit. In the above numerical, you calculate AV here only. Calculate AV without CE, without coupling capacitor CE. So what will be the formula over here? Anyone? Let's take some numbers and do it. AV is minus RC upon 1 upon GM plus RE. So calculate this number. It will be minus RC is 4K, meaning 4 into 10 is to 3. This will be 1 upon GM, which is 60.42 into 10 is to minus 3 plus RE. RE is 2 kilo ohm, 2 into 10 is to 3. So can you tell me this number? Similarly, calculate Rn. Rn was R1 parallel to R2 parallel to R pi plus 1 plus beta times Re. So calculate this expression first and then the others. And Ro is actually equal to Rc only here. So R out will be equal to Rc, which is 4 kilo ohm only. So can you tell me AV how much it is?
So is it minus 1.99?
Yeah, minus 1.98 something, right? How much it is? Minus 1.
So I got minus 1.99.
99 what? 0?
It's repeated 9 like 8 times.
Okay, almost minus 2 you're getting.
Yes, sir. Very close.
Okay, any other student got minus 1.99? Yes, no? Hello?
Sir, minus 1.983.
Yeah, actually I also got minus 1.983 only. Yeah, so the point is, when capacitor CE was connected, my gain is very, very high. And as I remove my capacitor CE, my gain drops to 1.9. This gain was unstable, 241, but this is stabilized gain, 1.9. What about Rn? Anyone calculated Rn? Earlier we have got Rn as 1.37 kilo ohms. Now you will get definitely higher than this. Can you tell me what's the number? It's 40K parallel to 10K parallel to RE is 1.655, 1.655 K plus beta is 100, so 101 times 2K. Calculate this Rn, how much it is? So this is definitely greater than 10 kilo ohms. So the answer will be less than 10 kilo ohms. How much is this? Anyone? Someone can tell me this answer? Yeah? Rn is how much? This is 1.655K plus 200K almost. So it will be less than 10K. So how many kilo ohms?
So is it 1.629?
I don't know. I don't have the value right now. For Rn at least. Can someone cross check this? Yeah, anyone else got this value? So how much is this number? Can
No.
you tell me how? This I guess it's 202 plus 1.6. So I think it is 203.655, right? So what is 40K parallel to 10K parallel to 206.55?
Sir, is it 7.92K?
7.69.
7 point something. How much it is? 7 point. Give me the answer. 7 point what?
Sir, I am getting 7.92 and he's getting 7.69.
Any other third person getting close to 7? I have a calculator, but it will take some time for me. So please tell me the answer. Any other person getting close to 7 point something? So 40K parallel to 10K will give me 8K. This is 8K, right? These two. So
Yes, sir.
8K parallel to 203. So 8K parallel to 203.655 divided by 8K plus 203.655. That's 7.697. This is what I'm getting right now. Okay. So the
Yes, sir. I
point
also got
being,
the same.
yeah, point being Rn has increased. Yes or no? And Rn increasing means it's a good thing for a common emitter amplifier. But the problem is the gain is reducing. That's the only thing which we have. So the degenerated common emitter amplifier, uh, we have found, I mean, the rest of all is same. How will you find Rn? The DC analysis remains the same. It doesn't get affected at all. So DC analysis is same. Only the AC analysis, the formula for voltage gain and Rn is different. Now I will show you for the last few minutes the derivation. So this document, I'll share it with you all. This is a detailed view, whatever we have done so far. Yeah, this is my degenerated common emitter amplifier. Yeah, we have built key pick. So we'll do the AC analysis. Then we replace the BJT by its hybrid pi model, right? No need to write this, you can refer it later. So we have got this. Okay, so earlier, remember, only difference is earlier emitter terminal was grounded. Now it is not grounded. That's the only difference. Okay, are you getting it? Now you apply your KCL at collector node. So once you apply KCL at collector node, what do we get? Two currents, GM into V pi, and here we have V out upon RC. So two currents are then a 1 and 2. Okay, so GM into V pi plus, can you see this PDF, everyone? Just confirming.
Yes, sir.
Okay, so just look at it. You just go through it. Don't write anything right now. So it is GM into V pi plus V out upon RC. So what will be V pi? V pi is minus V out upon GM RC. So called as equation number 1. So this is equation number 1. Now you apply KCL at emitter node. So KCL at emitter node is voltage upon voltage drop across RE, right? Here voltage drop across RE is what over here? VRE. Where how much is this? This is emitter current. This is IE into RE. Yes or no? Voltage across RE is IE into RE. And what is current through RE? Current through RE is two currents. One is V pi upon, this is V pi. So V pi upon GM, and another is GM into V pi. So here it is V pi upon R pi. Here it is V pi upon R pi, and here it is GM into V pi. These are the current through resistor RE multiplied by the resistor RE. That will become a voltage drop on RE. Okay. So now V pi upon RE plus GM into V pi. Now you substitute V pi from equation number 1. So from equation number 1, you substitute the value of V pi over here, V pi over here. Okay, so we get this next equation. All right, so your GM gets cancelled. That is equal to voltage drop across RE. Now further, if you analyze, you apply KVL in the base emitter loop. So KVL in the base emitter loops gives me what? Here it is V in minus V pi minus VRE is equal to 0. So what is it? V in minus V pi minus VRE is equal to 0. So VRE is voltage drop across RE, which is equation number 2. So you substitute the values over here. Okay. And what is beta? GM into R pi. So substitute the value over here of GM into R pi. So what you will get is this. Here you take the LCM, and finally you will get this formula. Now this is the exact formula. You can go through the mathematics later. This is the exact formula of V out upon V in. This is the exact formula for the voltage gain AV. Okay. We'll simplify it further. We'll divide by beta GM. Everything will divide by beta GM. So what do we get? V out upon V in is minus RC upon 1 upon GM. Divided by 1 upon GM plus 1 upon beta. Now normally beta is how much? Normally in the range of 350, right? 350 to 400. So what will be, let's say 381 divided by 380, it will be very, very close to 1, right? Yes or no? So 1 plus beta upon beta, can we approximate equal to 1 only? So that is what we have done. And we finally got this exact approximated formula. Minus RC upon 1 upon GM plus RE. Did you get it? Yes or no? Hello. So you go
Yes,
through
sir.
this derivation and we'll arrive at this voltage gain formula. So you go through this derivation. Next is input impedance. So input impedance is your entire circuit, you put it inside the box and you apply the Vx and Ix. So we have done that over here. Okay. So what we will do is, this is what we get out of the circuit. So we'll push R1, R2 branch to the left hand side of this. Okay. So we have pushed to the left hand side. Now we analyze this circuit. All right. So once we analyze this circuit, what is V pi? V pi is Ix into R pi. Okay, V pi is Ix into R pi, what we have written over there. Then we multiplied by Gm. So Gm V pi is Gm Ix into R pi. Okay, whereas Gm V pi is also IC, where IC is beta into Ix. Same. So current through RE is IE into RE. So what is the relation of IE in terms of IB? 1 plus beta times. So we have written over here IE is 1 plus beta times IX. So now we apply KVL to the base emitter loop, which will give me Vx minus V pi minus VRE is equal to 0 again. So we have written over here Vx minus, V pi plus VRE. So V pi is Ix into R pi and VRE is 1 plus beta Ix into RE. So over here we can club this term together. So we want Vx upon Ix, we'll get R pi plus 1 plus beta RE. But remember we have pushed R1 parallel to R2. So here we are getting R pi plus 1 plus beta RE. So if you look from here, what you will get? R1 parallel to R2 parallel to this term, right? R pi plus 1 plus beta RE. And that is exactly my Rn which we get. Okay. So here it is. Here is the formula for input resistance. Well, output resistance remains the same because if Vin is 0, then V pi will be 0, then Gm V pi will disappear. This will become 0. Okay. And you are left out with RC only. All right, for this. So therefore, output resistance is RC only. So you can have a look at it. Now, there is one important question which I want you all to go through it, the document. Why is the gain of the amplifier negative? Now we have said why the gain, what is the meaning of the gain of the amplifier negative, but why it is in a negative in the first place. So let's say that Vin increases. Okay, AC value, this is AC, this V out is also AC, this is DC. Okay, so let's say Vin increases, AC value increases, then VB also increases because over here we have AC plus DC at VB. So if AC voltage increases at the input, VB also increases. Okay. As V is a constant, V is a constant DC because here AC goes to the ground. Emitter voltage, emitter this thing voltage over here is constant. Since capacitor blocks DC values. Now what will be VB? VB is VB minus V. V is constant, so VB is increasing. That means VB is increasing. If VB increases, what happens to IB? Increases. From the graph, you remember? This is IB versus VB. So VB is increasing, IB is increasing. Okay. That means IC increases because IC is beta times IB. So IC increases because IB increases, therefore IC increases. Now, what is output voltage over here given by VC? VC voltage given by, at this point, it's VCC minus ICRC, the DC value of it. So right now we have IC increasing. So if IC increases from here, what happens to VC? VC, what happens to VC? Come on. VC reduces, no? Yes or no? Or VC increases? Increases or reduces? Come on, tell me fast. Hello. So here IC is increasing. So what happens to VC? VC will reduce. Here it is written incorrectly, it's reduce. So output will reduce. Got it? So if input is increasing, output is reducing. So therefore we say it's out of phase with each other. So like this, if this is my input, this will be my output. Okay, so this is V out, this is V in. That's why if my input is increasing, my output is decreasing. Okay, and they are phase of out of phase by 90 degree, and that's why it is negative. All right, so that's all for today. Let me stop the recording. So